So for the last talk of the day and for the last talk of Martin Kruczenski at this workshop and conference, Martin is going to talk about the S-matrix bootstrap in 2D and 4D, the primal and dual problem. So go ahead, Martin. I'll let you know when you're running out of time. I'll give you a 5-minute warning, okay?
Okay, thank you.
Okay.
And so you can see the slide, I guess, because you saw
Yes, we
the
can see it all.
title there. Okay, thank you very much for the opportunity to present this work. And if you were here or there, I mean, in the last week, some of the things will be repeated. Maybe will help clarify some things and some other different, I mean, some extra things that appear in some recent preprint I wrote with Ife, one of my former students who is now at the ENS in Paris. And so what I'm going to talk about, first I'm going to give an introduction or also motivation of the idea of this work. And the idea, the general idea is to map the space of allowed scattering matrices that you can have in a field theory with certain symmetries, allowed by constraints given by unitarity, analyticity, and crossing, so very generic constraints that have to be obeyed by the scattering matrix of any quantum field theory. And once you have that space and you try to characterize it and map it out, sometimes you can find distinguished points in that space that corresponds to given S matrices. And if you can identify those S matrices with field theories of interest, then you have a method to compute the S matrix of such a field theory. That works in 2 dimensions where we consider the ON model to compute the scattering matrix and also the reflection matrix, which appears when you put a boundary in the space and particles can reflect from the boundary. And in that space that I'm going to give some pictures, you find some interesting points. And at those points, you have the S matrix numerically in a very simple way from these very general constraints. Now, in this case, the matrix of the ON model in 2 dimensions was computed by Samological and Samological before using integrability. Here, we're not using integrability, but in any case, we're getting the same S matrix. And then we try to expand this to 4 dimensions to compute pion scattering. And as the previous speaker, the goal is always interested in trying to do a QCD. But in that case, we have some characterization of the space of S matrices, but identifying where QCD is, well, other than using the experiment, we don't know how to do that. So it will be interesting to have some general characterization of what general properties the pion scattering matrix obey other than the crossing analyticity and unitarity. And so let's start with the motivation. So in the 50s, there was a lot of I guess it was a very 50s, 60s, and 70s was a very interesting time. People didn't know for physics, I guess other things also, but people didn't know about strong interactions was the fundamental or basic description of that. And there are many interesting models like that gave rise to string theory, non-abelian gauge theories. And one of those models was the S-matrix bootstrap of Chu and Mandelstam and other Frauchi and many other people that was precisely saying that the S-matrix satisfies these general constraints from symmetries, analyticity, unitarity, and crossing. That if you consider that, you may be able to define or compute the S-matrix in a self-consistent way. Now we know that that's not true. There are many consistent S matrices, but recently Paulos, Penedones, Toledo, Van Ries, and Vieira, in a series of 3 very interesting papers, proposed a new version of the S-matrix bootstrap. In particular, they said that you can consider in the space of allowed S matrices certain functionals and define the theory by the S matrix that maximizes such functional. And in certain cases, for example, they found the S matrix of the Sine-Gordon model in 2 dimensions, and also the 4 dimensions maximizing, finding S matrices that maximize couplings. So the coupling that they were interested in was the coupling between a particle and its bound state. assuming a fixed spectrum. So if you increase the coupling, you tend to form more bound states, but since the number of bound states is fixed, you get a maximum coupling, and at that value of the maximum coupling, you get some S matrix that may or may not be of interest depending on your couplings and the theories you are looking for. But since that was the method, with the two former students, I decided to consider the ON model in 2 dimensions. This is slightly different from the previous ON model, the vector model, but it's, on the other hand, is very similar. It's a nonlinear sigma model, and the idea is interesting because this model has no bound state, so there is no coupling between particle and bound states that you can maximize. But we saw that you can still maximize certain functionals and get the ON integral model, the S matrix, but there were many functionals that maximizes that you can maximize to get the same model. And so the idea that we argue there is that there is a convex space of allowed S matrices that has a vertex. And suppose, imagine you have a cube and you put it on certain position and you look at the maximum, the highest point, it will be one of the vertices in general. And if you tilt the cube in different ways, the same vertex will be the maximum until you tilt it in such a way that it's another vertex. I mean, special cases, you will have a full face or something, but that would explain why there were several functionals that were maximized by the same S matrix. So why I'm arguing that this space is convex? Well, suppose you have the S matrix and you consider a subspace psi, whether of states psi d, and I apply the S matrix. I can separate the resulting state into projecting on the same subspace, for example, 2 particle states, and I call that the reduced density scattering matrix in the subspace plus some perpendicular state. But the norm of this state is less or equal than 1. So that means that the norm of this state is 1. That means that the norm of this part should be less or equal than 1. The space of matrices that satisfies that the norm of this state is less or equal than 1 for any state in the subspace is convex, because if I have 2 S matrices that satisfy that, and I make a linear combination with alpha between 0 and 1, that means in this infinite dimensional space of S matrices, I consider a segment between the two. Then the norm of S tilde psi, where psi is any state in the subspace, will be this. And S1 of applied to psi has norm less or equal than 1, so it's in a ball of radius 1, and so is S2. So if I make a linear combination or a segment between 2 vectors in a ball of radius 1, it will be inside the ball, and that means that this is less or equal than 1 for any psi, and that means that S tilde is in the space. So the space of allowed S matrices of reduced or S matrices projected to a subspace is a convex space. Then the general picture, I mean, this is an infinite dimensional space, but this is some sort of schematic representation of that space. These are all the allowed S matrices. The boundaries are given by unitarity constraints. What we say is there are some vertices and some vertex. For example, you have a free theory, you have an integral model, and you can have other vertices with other interesting theories. So let me discuss this 2-dimensional ON model. It has some characteristics similar to QCD, but it's a very simple model. It's a unit vector with n components, similar to the previous speaker, but here the length is fixed. That means that this represents a spontaneous symmetry breaking, but you cannot have that in 2 dimensions. So, so if you don't think much, these are n-1 Goldstone bosons that describe how the n moves around the sphere, unit sphere, but at low energy, the coupling grows and develops a mass gap, and you have the symmetry restored. So you have ON symmetry, you have n species of bosons with mass m, and you can compute the scattering in 2 dimensions that 2 particles collide and they can go through, or they can be reflected, or they can be annihilated. And there are 3 functions of the energy, of the center of mass energy, the Mandelstam variable, the only one you have in 2 dimensions, that give you the amplitude for annihilation, transmission, or reflection. And crossing symmetry gives you a relation between the transmission and reflection at different points, but if the S should be real and larger than 4m squared, but I'm putting m equals to 1 for a physical scattering, so this relates physical to unphysical regions. And so the thing to do here is to analytically continue the Mandelstam variable S. And in this analytically continue variable, then this crossing, there you can have these analytic functions with these crossing properties. The other thing is that you can consider scattering a given isospin channel. So when A and B, the initial particles are coupled to zero isospin, or the symmetric traces or anti-symmetric representations. That's suppose you have the isoscalar, that's the only isoscalar state you can have with two particles, so it can go to itself or it can go to more particles. And therefore the probability of going to itself has to be a complex number with modulus less or equal than 1, and the same for the others. This we want to find all the possible space of these functions, but it's an infinite dimensional space. So what we do is we take a section, if you want, just two-dimensional. This is here, I don't know, you can see here a small plot of the analytic structure of these functions. So you have a cut on the real axis from 4m squared to infinity. These are the two particle states. And you have a cross cut by crossing symmetry. Well, m is supposed to be 1, I was saying. So s to 4 minus s gives this cut. And I consider this point. Principally, I can consider any point, but at this point of the unphysical, there will be unphysical. This is a physical line, so this will be an unphysical point. But there, the annihilation and reflection are the same, and the transmission, well, is different. So we could ask in the space, all space of allowed functions, and allow just by saying that the modulus square is less than 1 at the physical line for the isoscalar plus and minus representation, and allow by the crossing symmetry and analyticity. So I'm not imposing any other constraint. The allowed values of these analytic functions at that point is given by this shaded region here. And if you look at this shaded region, there is some obvious distinguished point here, and this corresponds to the free theory. The transmission is just 1 and there is nothing else. And if you look more carefully around this point, it looks smooth, but if you magnify around that, you see some vertex. And at this point, you can see what S matrix lives there by taking, suppose, a linear functional that points in that direction. So when I maximize it, I find this point. And if you do that, you get the scattering matrix of the ON model, the integral ON model, which is already known, as I said, but here we just derive it numerically from this simple consideration. So we didn't use almost anything. The caveat is that in a general situation, you have all these, for example, points, and you don't know which one is your theory of interest. So you have to use some other information. Here we know what the S matrix of the ON model is, so we can try to look for it among these points. Now, this is another example just to show how things work. So this is a reflection. So I'm not going to discuss much, but when you reflect from a boundary, you have also different functions or reflection probabilities. These regions give you the allowed space of functions. And for example, you have some vertex corresponding to Dirichlet boundary conditions when you fix the value of the fields at the boundary. And that's all you see. But here, the only thing, the reason I'm saying this is because we can use another technique, which is to expand or enlarge the number of constraints, which reduces the space of allowed functions. And in this case, we increase the analyticity region, saying, well, we don't have any bound states, so we don't have any poles in the physical sheet, but we're going to go to the next sheet and say that there are no poles there in a certain region. And when you do that, the space is reduced and you get this region, for example, the orange. And now we see a vertex that corresponds to the Neumann boundary conditions. Sorry. because there is no pole in that case in this extra analytic region of the second sheet of the S matrix. So that means that you have to be clever to find your theory, so you can use the basic constraints, but then you can enlarge them, for example, add analyticity, add any other constraints that you may know your theory satisfies. And when you apply them, you try to reduce as much as possible the space of allowed functions, and hopefully you can find the theory you want. And here I'm just giving an example, for example, in case of reflection, that one can also compute analytically. For the ON model, the agreement between the points, which is the numerics, again, using no other input, and the solid curves, which are computed using integrability. Okay, so how do we map this space of functions? So this one way to use these things that we call generalized dispersion relations. That simply goes as follows. So suppose I want to compute the value of these S matrices at some point S0 with these cats. I can put a circle around and integrate 1 over S minus S naught. And by the Cauchy formula, I can deform the contour. I can get the value there, and deforming the contour, I get this as an integral given by the jump over a cat. And the observation we made is that you don't have to put 1 of S minus S naught. You have to put an arbitrary function that has a pole at that point of residue. In this case, let's say NA, if I want to maximize some linear combination. By maximizing different linear combinations, I map out the boundary of this space. But the thing is that I don't have to put 1 over S minus S naught. I just need to put a function that has a pole there, but can have cuts, because I'm not going to deform the contour across the cuts. So this function K can have cuts in the green lines, and the function will still be given by the integral of the jump on the cut. And the jump, if I do the define this appropriately, the jump is in the imaginary part, and the two cuts are related. So I'm going to just integrate over one cut. I mean, this is some detail, but the main point here is that once I do that, I get the functional, so the S matrix evaluated at a physical point given by an integral over the physical line. And in that case, I can use unitarity, so the imaginary part of any function is less or equal than the modulus, but the modulus of this S matrix is less or equal than 1, so I get a bound based on these functions and with no S matrix anymore. And therefore, the maximum I can get for this functional over the space of all S matrices that give me the boundary of that space is less or equal than the minimum over all the space of KAs. And these KAs we call the dual S matrix or the dual partial waves in higher dimension. And there is a theorem that says that these two are equal, so I can put a lot of functions KA here. And from those, so with some clever answers, I can try to find the minimum. And in that way, I can map the allowed space of S matrices, because I can find the largest value that different functions have, and that maps the boundary. And that's how we did those plots that I showed before. Okay, so I think I have some little time where I can discuss higher dimensions. In higher dimensions, we cannot compute exactly these S matrices. Well, we can compute some S matrices, but not for the moment that corresponds to some particular models of interest. Let's consider the language of pion scattering, so scalar field scattering. And I'm going, for this purpose, consider pi naught, just one pion. And the scattering is two particles come in, two particles go out, and I write it in terms of the Mandelstam variables. I have a scattering amplitude, and the scattering amplitude in Mandelstam representation is written in terms of a single variable spectral function and a double spectral function rho. And it has the property by crossing that this is completely symmetric under the interchange of ST and U. It's convenient to write it like this, although ST and U are not independent variables, they add up to 4. This has cuts for ST and U larger than 4, which are the two particle cuts, the same as in 2 dimensions. So Mandelstam proposed this representation. This is not proven for arbitrary field theory, but it's a good basis for analysis. And the other thing is, as you know from quantum mechanics or quantum field theory, you can write the initial and final state in a basis of angular momentum. And for each angular momentum with two particles, you have only one state. So once again, there is a scattering matrix to scatter in that angular momentum channel, which is just a number. And the model has to be less or equal than 1. It can also be written as a 1, which would be the free theory, plus something that depends only on the interactions, which is called the partial waves. It's also written in terms of the phase shift e to the 2i delta L times some eta L, some real number, times phase, which is the phase shift. And if you know the scatter in each angular momentum channel using the Legendre polynomials, you can reconstruct the amplitude. So these are usual formulas. These are not going to go into details in this slide, but I want to remark that the forward scattering, which is theta equals to 0, 0 scattering angle, t, the Mandelstam variable t is 0, and then u has to be 4 minus s. So you get a function of s that has symmetry s4 minus s. So it has the same analytic structure and properties than the two-dimensional case. So you can use these techniques with this kernel that I said before. So one way would be to concentrate on the forward amplitude, and that's one direction we are in which we are proceeding now. So just look at the forward amplitude, see what we can do there. Then you can consider the whole amplitude function of S and T. And there are several regions to consider. One is S larger than 4 and negative T from 4 minus S to 0. That's where physical scattering with physical energy and angle happen. And then there is a region S bigger than 4 and T bigger than 4, which is where the double spectral density has support. And this is different from two dimensions where both the regions were the same. And that, I mean, seems not very important, but produces some complications. And in this recent paper, last year paper, we extended the ideas of this extended analysis, the generalized dispersion relations to 4 dimensions based on some simple complex identity that we found for any analytic function of 2 variables defined in terms of double spectral density. One can compute the double jump, as it's called, and from there you can compute this interest should be 0, because if you integrate over a contour like this has only singularities on the real axis, so any integral like this will be 0. So using these two things and defining G as the product of the amplitude and this K, which we call the dual amplitude, we found this that this particular combination reduces to this type of integrals and then is 0. And this combination has a double jump of the amplitude that has support in the Mandelstam region S bigger than 4 and T bigger than 4. And we put the dual amplitude to such the double jump has support in the physical region. And therefore, this integral, this part will contain the amplitude in the physical region that is bounded by unitarity. And this we can put some delta function that give, here we can put some delta function, and some delta function here that give you the value of the H at some unphysical point. And that relates the value of H at an unphysical point to the physical values of H that can be constrained by unitarity. So, I mean, maybe I don't want to go into more detail, but here you can find the idea. So you have the amplitude in the physical region where you can use partial waves and impose unitarity on the partial waves, plus a term that has a delta function and give me the value of the amplitude at an unphysical point. The difference with 2D, so we get some extra term from the double spectral density and this dual amplitude in the Mandelstam region that we need to bound by putting some regularization of the double spectral density. So in the end, what we get is a formula similar to 2D. This here in 2D was modulus of KL, but that's just from the definition of the partial waves. So these are like dual partial waves. Because we're not putting SL, but we're putting the partial wave, there is an extra term that gives you the real part. The upshot of this is that if you take dual partial waves and they don't satisfy any constraints, they just put them in this formula and try to find arbitrary functions here and minimize this integral. That will give you the maximum value that the amplitude can have in some unphysical point here for the in the ST plane.
5 minutes,
So
Martin. 5
sorry,
minutes.
5 minutes. Okay, good.
Okay.
So thank you. So then we get this functional, which in terms of the dual partial waves. Once we find the dual partial waves, minimizing this, we can compute the actual partial waves, the HL, and they should satisfy crossing. But the dual partial waves do not satisfy anything. So that's interesting. And by using that method, we can find, for example, the maximum value that the amplitude can have at the symmetric point. And by introducing more and more dual partial waves, we reduce the value up to the known value that was computed. Well, there were many people over the years computing this maximum value. The latest result from that paper of Paulos, Penedones, Toledo, Manriz, and Vieira, where they started this, also studying this matrix in higher dimension, and these methods agrees with them. And whenever you reach the maximum, you can compute, before I was saying the S matrix, in this case, you can compute the partial waves. The idea would be to find some partial waves that corresponds to your field theory of interest. So if your theory of interest is QCD, this is not your theory because this theory, the maximum of the amplitude, is found by a polar threshold. So you have like a bound state of a threshold. So it's not really bound, but it's kind of a bound state with zero binding energy. And that's the amplitude in the S wave channel, and that's the amplitude that maximizes the value at some unphysical, at the symmetric unphysical point. And QCD does not have any bound state of pions at threshold, so that's not the theory. But the idea is to keep looking and to find some more constraints and see if a QCD can appear from here, or maybe some other theory that in 4 dimensions that you might be interested in. Now, this is once again, S and T, this is the small Mandelstam triangle, and you have this symmetric point. No, sorry. Symmetric point is 4/3, but you can go along this line where S and T are equal and maximize, see what's the maximum value that you can have for the amplitude, and we got this curve. This is some new result. I don't think it was computed before. There were some points that were computed in the 70s. The symmetric point in particular here, 4/3, and but here we find the whole curve. So any physical quantum theory of scalar particles, the amplitude of scattering in this unphysical region has to be smaller than this curve. For example, you can zoom, but it also has a minimum. The minimum is harder to compute. This theory seems to be more complicated, but any quantum field theory has a scattering amplitude in that unphysical region between this value minimum and this value maximum. So the minimum is negative. So once again, the idea is to map out the space of allowed functions, and here we are just characterizing these functions by one value at some one point, and then you have a range that it can have. And if you look at different points, you have all these allowed region. One interesting observation, which is for the moment numerical, is that the minimum, the amplitude that gives the minimum for any point inside this segment looks the same. So if you plot it for if you plot the amplitude for different values of S, you get the same curve. So it seems that there may be some universal amplitude that minimizes the value at a given point, but that's just numerical. And you can extend this to 3 pions, which is what we are more interested in. And once again, we find these allowed regions with vertices, but these vertices do not correspond to QCD. QCD seems to live here more in the middle. So you need to somehow reduce the space or project it into different directions to find a QCD. But this, we also did not identify these vertices. I mean, we can compute the S matrix, but we don't know if they correspond to any quantum field theory of interest. Okay, so to conclude, there is a new version of this S matrix bootstrap of Chu and Mandelstam, which is to define a field theory by finding some distinguished point in the allowed space of S matrices. And those can be found by maximizing linear functions in convex space. There is many good numerical packages for doing that. They are free for academic use. But the main point is, how do you find your field theory among all those allowed S matrices? So you need to find some properties of your field theory that you can characterize in terms of the S matrix, and use it to reduce this allowed space and hopefully identify there. Once you identify your point, then you have the exact, well, not exact, but very precisely S matrix computed numerically. Okay, so that's all, and yeah, I'll be happy to answer any questions. So I guess we are finishing the day, so maybe.
Thank you, Martin.
Yeah, it's very interesting, but we know in QCD that the pion mass is an arbitrary parameter, and it's a perfectly good theory as that gets arbitrarily small. So if you would take the pion mass to 0, would you get any constraints?
Well, yes. So there is a papers by precisely by Penedon and Vieira, or some of the same authors that started this, where they consider massless pions, and they try to constrain the coefficients of the effective field theory that you get.
No, but in your approach, that would shrink this triangle to 0. Wouldn't that weaken
what happens is that you will have for example, this cut with these two will connect, but there's still something in the middle. So what you get is logarithmic singularity. So you get the log S, and you have the coefficients of those log S you can constrain. So you need to be more precise on the analytic structure.
The other piece of information in this limit is we know that the low energy theory is exactly the chiral Lagrangian, because we have chirality, and the pions are not just normal particles, right?
Yes.
So,
yes.
I mean, I think QCD is a family of theories with a chiral Lagrangian as the low energy limit. And there's, you can't even define that mass except for with respect to some other mass, which is usually the lambda parameter. So,
yes.
I mean, it seems to me there's physics
yes,
you have to put in to get close to having it constrained.
Yes, so you have a parameter, a dimensional. So here we're putting the mass equal to 1, so the pion, but you have an adimensional parameter, as you said, which is the ratio of the pion mass to lambda QCD, or in physical terms, you can do pion mass to, for example, nucleon mass, or you can put, yes, that's the thing you need to think. For example, you can include some scattering length. So you can say, I want to require that the scattering length in the S wave agrees with the experiment. And then we are putting the dimension full parameter. So then you will have the ratio of that with the mass of the pion. And so the question, should we include that, or should you include, for example, the mass of the row as data? So you would like to extract as much as possible, but you have to put something else. As you said, you need something that sets the scale of the pion mass with respect to lambda QCD. And so how much are you, but even if you put the correct scattering length, you don't get just a unique
I mean, the point is, as you say, there's a family of theories that would satisfy all of this. Any pion mass, any n, color n,
yes,
will satisfy all the statements you're making, right? So
yes,
clearly,
yes.
You're not going to get a unique theory.
Yes, so the question is, what else are you willing to add as information, right, and what's the most constraining thing you can add? Yes, so you could require the raw pole, or you can require, as I said, scattering lengths, or you could require the full P wave phase shift or something like that. Yeah, we don't know.
Martin, is there anything that can be said about the Wessel term?
in 2 dimensions? Or what?
More like in 4, because that's something that would fix n in some sense. So,
What Weismann term? Sorry. So you in the pion Lagrange?
well, it's a
you
5
mean?
pion thing. So it's not really
Oh.
5 pions. It's pions and extra particles. But yes.
Yeah, no, I don't know that. Sorry. Yeah, that would be nice to look if there is a way to include n. Yeah, the way some people thought about including n is to look at the central charge, at the UV theory. So in principle, one could look at impose something about the central charge, but that seems very hard. But this Weismann, yeah, I don't know how that works. Sorry, but that's it would be. I will look at that.
Anyone else? Okay, let's thank Martin.
Okay, thank you for this very nice conference, and